Welcome to my talk about practical partial evaluation for high-performance dynamic language runtimes. So first, what are we trying to solve here? The world is polyglot, and it's becoming actually more polyglot almost every day. Evidence for that is in the TOB programming language index. So this is taken from the data taken from the latest TOB index from May 2017. And what you can see is there's really not one programming language that dominates everything, but the programming language space is actually becoming more diverse. So there's more and more programming languages popping up, and more, the share is more and more evenly distributed. And the problem with programming languages, and in particular their implementation, is that it's a fairly complex and resource-intensive problem. So often when you create a programming language, the first thing you would do is you would create a parser for your language, and you would create an EST interpreter for your language. But then at some point you actually need a real VM, you need like a garbage collection, you need to have a runtime system. Then people are complaining about performance, and your EST interpreter will not be fast enough anymore, so you will move over to a bytecode interpreter. And finally, you will, when your language gets really well adopted, you will have to create a JIT compiler and a better garbage collector. So it's becoming a lot of effort. And if you look at very famous programming languages like, let's say, Java or Python, then both of them have gone exactly through those stages. So also for Java, it started off more with an interpreter approach until the JIT compiler was created. And it unfortunately requires a lot of investment, and that's, I think, at this stage, prohibiting some of the innovation in the programming language space. So our vision here is that the first step should actually be enough. After you created a parser for your language and you created your EST interpreter, you specified everything about your language that is necessary to specify, so the rest is something that should really be automated, and you should not have to do anything to do with that. We started out with that vision about 4 years ago, where we published a forward-looking work-in-progress ideas paper on one VM to rule them all. And I'm now happy that I can, 4 years after putting the ideas onto the ground, present some of the results that we have achieved in this time. So our work is mainly based on the first Futamura projection. So the first Futamura projection says, when you specialize an interpreter for a given source code, you get an executable. So for us, what this means is that when I'm running a function in our system, well, you can interpret it, which means you will call the execute method on the function, or you can run the compiled version of the function by first doing a partial evaluation of this execution function. And so I'm partially evaluating the execution function, and the element that is constant is the function itself. So I'm specializing the function, I'm specializing the interpreter, the execution of in the interpreter for a specific function. And then I get back the compiled version of that method, and I can run that. So during this specialization, or during this partial evaluation, we are inlining through the whole EST interpreter. So we have a very aggressive inlining policy here, which says inline everything. And but so the first thing that needs to be considered in the context to make this practical here is that sometimes you might have something in your interpreter that you actually do not want to include in your compiled code. We call this a partial evaluation boundary, and the equivalent in a traditional virtual machine is a runtime call. So a traditional virtual machine like Hotspot or V8 would create an assembly stop with a runtime call, and our equivalent to that is to just tell the partial evaluator to stop this aggressive inlining. And this is important in order to reduce the machine code size. But so there's two more things that we introduced in order to make this practical. And I want to mention here that the work is mainly inspired actually by a sentence in the paper of Futamura from the 1970s, where he says, well, we think this could work, but we're not sure if it will work in practice. And what I'm presenting here is the elements that make it work in practice. The second element, and because we are focused on dynamic language execution, the second element that we introduced to make this partial evaluation work in practice is local speculation. So what we do is that one of the things you can do with variables is you can say like they are partial evaluation final, which means the compiler during partial evaluation will assume those fields and those variables as constant. So I have a little bit an example of a dynamic language construct that implements negation of a value, and it has like a fast path on top that is checking whether the incoming value is a number, and only if the incoming value is not a number, I go into the slow path. But then in my compiled code, when I do the partial evaluation, I actually want to speculate that my fast path is occurring. So therefore, in the slow path, I'm checking whether I've ever seen that object, so whether object seen is true. And if it's not true, I just cut off this control flow path. I just say, here, like, if you see this place, go back to interpreter. Exit your partial evaluated code, go back to the interpreter. And but once you go to this place and you see it for the first time, then you set the variable and you handle the slow path. And this means that if you, at a certain operation, you only hit the fast path, then the code in the compiled version will look a little bit like here on the right. So it will speculate that the value is a double, and if it's not a double, it will move back to the interpreter. And the slow path is cut off. Here again, we are cutting off again a part of this partial evaluated tree. And only if I hit the case, then the compiler will build this type of construct where it will compile the slow path into the program. And the most important aspect here is that the compiler does all of this automatically without ever knowing about the concept of negation in that language or without knowing about the concept of how the profiling in that language works. So our compiler is completely agnostic of the language and completely agnostic about the profiling strategy of the language. And this then allows the languages to be innovative in terms of how they are expressing their profiling. So this is, after partial evaluation boundaries, this is the second primitive, and the third primitive that is necessary to achieve high performance for these dynamic languages is something we call global speculation. A global speculation means you're creating a speculation about the program state as a whole. And in this case, I'm assuming I have a language like Ruby where you can redefine the addition operator. And here, I have like this fast pass addition of two numbers, but this is only true or only valid to execute if I have not overwritten that function. And in this case, in our interpreters, we are checking this assumption flag. So when it's running an interpreter, it is checking that flag, and when somebody redefines the function, the flag is invalidated. And this invalidation again causes the optimization. So it again causes the compiled code to go to the interpreter. And this means that in our compiled code, we do not need any check for the addition itself, because we will register, we have a global registry where we say this compiled code needs to be invalidated if that assumption is invalidated, right? So we are connecting the assumption with the compiled code. This is something like traditional VMs like Hotspot do for things like class hierarchies. So Hotspot would register the assumption that a certain class doesn't have a subclass. So the difference in our case here is that, again, the runtime system itself has no knowledge, no semantic knowledge about what this assumption actually means. Because in Hotspot is limited to like 6 assumptions or something. Like you can have like a final method, a final class. And these are all baked into the runtime system. Introducing a new one of those assumptions is very hard and very intrusive. In our system, the interpreters are completely independent from the runtime system, and they can themselves define their own assumptions. And this allows them to create more complex assumptions. We have, for example, an R implementation where we are creating like thousands of assumptions on one method, because the implementation is so complex and needs to speculate on so many things. So that is the third primitive that we introduced to make this partial evaluation, this language agnostic partial evaluation, possible. To show you here a little system overview of how this approximately looks like is on the left you have like an interpreter running, there is like parts of it's an EST interpreter, so it's nodes or methods calling each other, and the interpreter, there's also a runtime code which is associated with the interpreter. And when then a certain part of your language gets hot, a certain method gets hot, we partially evaluate through that interpreter call graph and create one compiled version of that function. We never partially evaluate through the runtime code because the runtime code is kind of our runtime stubs that are only called once. And this compiled code can either call into the runtime, or if there is a de-optimization, a speculation is failing, this compiled code can jump back to the interpreter. And there can be many, many versions, many partial evaluations of the same interpreter entry. Basically, the same interpreter entry is partially evaluated as often as many hot methods of that dynamic language or of that interpreter you have. And it's interesting that like with these three primitives, you can do a lot of complex constructs without changing the underlying runtime system. So one of the things that's very easy to implement in our system is custom inline cache structures. Usually inline caches in V8, for example, they have like a certain way how they are gathering the information in the baseline compiler and then transmit it to, or the interpreter nowadays, and transmit it to the optimizing compiler, but it's all baked into the runtime system. In our case, only with this a few primitives like this partial evaluation final and with the de-optimization, we can build our own inline cache strategy without ever like leaking this abstraction to the compiler. So I'm kind of just creating here first an uninitialized entry. That means it was never executed and it just goes to the interpreter immediately. And then I can chain actually cache entries, where my next entry is always the entry that is constant, because that's the entry I'm partially evaluating through. And if that chain gets kind of too large, then I can then move back to a generic entry. So I'm kind of changing the chain of inline caches, and no matter how the chain currently looks, once the chain stabilizes and the method gets hot, the compiler will create exactly the code according to the structure of the shape. So if I could put, like for JavaScript, for example, you can have multi-dimensional inline caches because you have like a prototype chain as well to consider. And then in this context, you could just make a two-dimensional tree here instead of this one-dimensional list, and I will immediately have my own custom two-dimensional inline cache for my language. The other thing that is almost trivial to implement in our system is OnStack Replacement. So OnStack Replacement is trying to create compiled code at a point in time when a loop is executing often enough that it's worth to compile the loop before re-entering the method. So the way we implement OnStack Replacement is, like, we have one primitive here, which is like an intrinsic, which is actually asking here, am I executing at the moment in the interpreter, or am I executing in the partial evaluated code? And so this in-interpreter code is, here we can see that we can specify our custom profiling here. And this branch that is guarded by in-interpreter will be removed in the compiled code. And in this interpreter branch, we are counting how often the loop was invoked. And if the loop is invoked often enough, we trigger a partial evaluation of the loop's body. And in this way, then execute the compiled version of that loop body. So this is just to show you how these three primitives that I was introducing before, partial evaluation boundary, de-optimization, and assumptions, can be used to actually build sophisticated runtime systems on top of this VM, including manual strategies for OnStack replacement. And at this stage, like if you would modify the OnStack replacement mechanism in a virtual machine like Hotspot, you will need like a very long time until you can do that or even understand the code that does this type of mechanism. In order to show that what we're doing here is not just, it's actually working in practice, we created three different language implementations, one for JavaScript, one for Ruby, one for R. Those language implementations are fairly complete. So for JavaScript, we pass all of the ECMAScript 6 tests. For Ruby, we are passing a very large fraction, above 95% of the Ruby specification. And for R, we can also run larger non-trivial programs. Each of those language implementations still has a significant amount of code. So because there's still a lot associated with just implementing the language semantics, but one of the largest components in the system, like the compiler that actually does then the optimization, is shared completely between those language implementations, and it does not have any knowledge about those language implementations. So I do never need to modify the compiler when I'm doing a modification in the language implementations. The partial evaluation itself is fairly trivial. It's only like 30,000 lines of code that does this type of like inlining and partial evaluation. We measured our performance relative to some production systems. And so the first system we measured against is the V8 JavaScript engine. We thought this would be a good target to measure against because V8 has received a lot of engineering effort to optimize it for JavaScript specifically. And so we thought, well, if we can get near V8, that will be a proof that despite our abstractions and despite our multilingual approach, we can compete with a highly specialized production quality virtual machine. And yeah, we are a little bit slower at the time of submission of the paper, but now actually we have improved a bit, but it always depends on the set of benchmarks. So we have some benchmarks that are even faster than the specialized virtual machine. We also compared against JRuby. JRuby is the approach of generating bytecodes for Ruby on top of the Java virtual machine. And versus JRuby, we can see a larger speed up. One thing is, of course, JRuby hasn't had the same level of investment as let's say V8. And this is also kind of a result that shows these differences about how the bytecode generation approach to execute languages on the JVM, how this semantic difference between JVM bytecodes and Ruby is creating problems in terms of performance for a Ruby implementation that is creating bytecodes. And we also implemented R as a very different type of language. It's an array programming language. It's actually the hardest language for us to implement because the amount of speculation and optimizations we have to do in this language is the largest. And but there we get, of course, like a large speed up because R is running only in an interpreted mode. So this is measured against the R bytecode interpreter with a rough 5x speed up. But it always depends on the benchmarks. If somebody wants details, I can show you the detailed results. Because in particular for R, for example, it differs very largely on benchmark per benchmark basis, whether we get like 100x speed up or only like 2x. To conclude this, so we think that our multilingual VM approach here has achieved the competitive performance with specialized monolingual dynamic language runtimes. And we've shown that for R, Ruby, JavaScript. And we believe there is 3 core primitives necessary to make partial evaluations, to make the first Futamura projection practical in the context of dynamic languages. And the first one is the partial evaluation boundaries. The second is the local speculation via the optimization guards. And the third is the global speculation, which are these assumptions. Future research, well, we now addressed the first Wuerthinger projection. What about the second Wuerthinger projection, which is specializing the specializer for the interpreter as applied in the first projection and yielding a compiler? And this is actually interesting because we're already going a little bit in that direction, because once we can specialize the specializer for a specific interpreter, we might be faster in our compilation process. It's kind of, you speed up your compiler this way. So this is a very large project, very large research project that's running for like 4 or 5 years now. And there's a lot of contributors around that project that has helped make that project successful, as well as academic research collaborators that have tested various parts of the system and created their own research on top of it. And that's in general an invitation also to you to use our virtual machine also as a research artifact. What we can give you as advantages over other places is that you can do compiler type work without actually hacking the compiler. So the higher levels of the stack, you only need to kind of experiment in the interpreter only and get very good results and very interesting results. And the second part we can offer here is that we actually have complete language implementations for Ruby, R, and JavaScript. So any type of research that wants to be more broad in terms of the languages it addresses, if it's done on the core of our platform, you can immediately run non-trivial programs in those languages. That's it. Thank you for your attention, and I'm happy to answer your questions.
Instead of using the second Wuerthinger projection, have you thought about using generating extensions? So maybe 15 years ago, there was a project at CMU which dodged the complexities of specializing the specializer in that way.
Okay, that's interesting. Let's talk afterwards. It will be interesting to hear that point, yeah. But that's definitely an area we want to address because this might help us with improving the performance of the partial evaluation.
Your vision is that I just get to write my simple tree interpreter and then I get a fast VM. In your example, I think you were thinking about Ruby, you noted that, oh, I'd like to special case the plus operator. So that's not how I would naturally write the Ruby interpreter. I would generally just look up what's the current plus. So can you tell me, how many times do I have to do this special case to get to the performance that you're showing?
Right, yeah, good question. Yeah, so it is true that you cannot just write your interpreter without the profiling in mind. We give you the tool that you can do the profiling on your own, but it's really that the language semantics itself, at least in our system, right, is not enough to automatically derive what profiling would be the best. I think future research that would build on top of that system could be even more sophisticated, that would kind of potentially execute traces. Like another very related project actually to ours is the PyPy project, where you have to write less specializations, but you still need annotations as well, right? So I think completely deriving that automatically is very hard. It's interesting future research. In our case, we give you a set of primitives that make it easy, and we give you a domain-specific language that actually allows you to specify this in a more natural way. But you need to specify your specializations in that domain-specific language.
Hi. You talked about performance, mostly regarding the time it takes to execute the programs. It's much faster. But I wonder how it compares regarding memory consumption. All the framework, how does it compare to other systems?
Okay, thanks for the question. So memory consumption, like I don't think we have a big issue with memory consumption per se. We need slightly more memory during the partial evaluation process because we are inlining more than, or like we are using more abstractions during the compilation process. The largest issue we have at the moment, really, when we compare, let's say, with V8, is the compilation times that are at the moment a lot better in V8. But this has to do with our compiler having to deal with all these abstractions and doing a lot of escape analysis and other types of high-level optimizations before it can derive from the interpreter this specialized, this partially evaluated version, right? So I wouldn't say that memory consumption is not an issue. It's pretty much the same. So we have no restrictions there compared to other systems, but the compilation times is one restriction. And one of the ways we will try to address it in the future is this going for the second Futomura projection on specializing the specializer. Thank you.